So a piece of copper of mass 2 kilograms at 100 degrees Celsius is quickly transferred to a block of ice at 0 degrees Celsius without heat loss. Determine the mass of ice that will melt. Determine the mass of ice that will melt. The specific heat capacity of copper you are given as 400 joules per kilogram per Kelvin. Latent heat of fusion of ice 3.3 times 10 to the power 5 joule per kilogram per Kelvin. And the possible answers are there. So I want to see how you can attempt this problem within 5 minutes. It's 10:06. Start work. 5 minutes. I've highlighted on the question. Agreeable, mute yourself. Time is up. Let's see what you managed to get. Yes. Whoever managed to finish, let me hear from you. What is your final answer? Whoever finished. Oh, let me hear from Stephanie.
Then please, I had 0.242 kilograms.
So Stephanie had 0.242 kilograms. Okay, who else? Who else managed to finish? Charlotte.
Please, I also had 0.242.
So same answer.
Yes, please.
Anybody else? All right, let's see. So the question, let me retrieve the question. The question says that a piece of copper of mass 2 kilograms at 100 degrees Celsius is quickly transferred to a block of ice at 0 degrees Celsius without heat loss. Determine the mass of ice that will melt. So since the copper is at a higher temperature, heat loss by copper at 100 must be equal to heat energy, to melt ice at 0. And because the initial temperature of the ice is 0, any extra heat energy gain will melt it. Its temperature will not change, but because 0 is the melting point of ice, any heat energy gain, okay, heat to melt ice at 0, okay, any heat energy gain would begin melting it because we are at the melting point of the material. Therefore, mass of copper times specific heat capacity of copper times the change in temperature must be equal to latent heat of fusion. And this must be MLF. Okay. Now, what is the mass of copper? 2 kilograms. So 2 kilograms times specific heat capacity of copper, which is 400 times the change in temperature, 100 minus 0. 100 minus 0 will be equal to mass of ice times the latent heat of fusion of ice, which is 3.3 times 10 to the power 5. Therefore, mass of the ice must be equal to 8,000 divided by 33,000. 1, 2, 3, 4. 1, 2, 3, 4. So we have 8 divided by 33. Class, what is 8 divided by 33?
0.242.
0.242 kilograms. So Stephanie and Charlotte, you got it spot on.
And Nana too. She sent a message.
Oh, okay. Okay. So that's it. That's it. Now the other question I want you to try is the same NOVDEC 2022 question. And it reads, please listen. The same question, okay, but NOVDEC 2022. In a cooling experiment, 250 grams of water at 50 degrees Celsius releases 30.5 kilojoule of heat energy in attaining a steady temperature. In a cooling experiment, 250 grams of water at 50 degrees Celsius releases 30.5 kilojoule of energy in attaining a steady temperature. Calculate the final steady temperature attained. The specific heat capacity of water is given as 4.2 times 10 to the power 3. So attempt this question also in about 4 minutes. 4 minutes.
Mr. Dear.
Hello.
Please, is the question in the group?
Yes.
Please, can you
But Charlotte, I told you that I've sent a lot of Wassce questions, Wassce and of their questions into the group.
I just didn't know the particular one you.
So I've forwarded it.
Okay.
So is the B question. In
Yes,
a cooling experiment, 250 grams of water at 50 degrees Celsius releases 30.5 kilojoule of energy in attaining a steady temperature. Calculate the final steady temperature attained if the specific heat capacity of water is given as that. In 5 minutes. Still 5 minutes. Stop work. So answers. Let me get your answers. Yes. Aba, Aquia, Watima, Ama, Annalyn, Alvina, Eura, Idrusu, Loku, Lizzie, Lois, Nana. Yes. Ooh, okay, Pierre Boatman got 20.95. So 20.95. By Pierre Boatman. Who else? NSMQ. I'm sure a lot of you could not finish the question within the time. Stephanie.
Please, I had 79 degrees Celsius.
79 degrees Celsius. Do we have any?
Let's stay there.
Charlotte.
Please, I had 50 degrees Celsius.
Yo, 50. All right, so let's go through to just Amma.
Sir, please, I got 50.03.
50 points.
0.
50 or 60.
50.03.
Okay. Equia 45.9. I'm at 50.0. Okay. Let's see.
I have a question.
Yeah, real.
So I got 50.029.
Okay, so you are also within the 50 range. Let's see. Alvina. Her last one.
Sir, 50.3.
All right. Okay. So you're also within the 50 range. So in a cooling experiment, 250 grams of water at 50.
Mr. Dia,
Hello.
please, I have a question.
Ask your question.
Please, when there is a change in temperature, is
Mhm.
the final minus the initial?
Yes. But you see, when there is equilibrium, the body that is losing, the temperature at equilibrium will be less than the body that is losing. Now, the body that is gaining, okay, because the body is gaining, the final temperature of the mixture will be greater than the losing body's initial temperature. So let's see how we will go about this. So mass of water 250, initial temperature 50, releases this amount of energy, okay, in attaining steady temperature. Calculate that. So it's like heat loss by water at 50 degrees Celsius must be equal to heat gain by the environment. Okay, but let's also look at heat gain by another body, maybe another body by body. Okay, and we are to determine the steady temperature. So let's calculate the heat loss by water. So mass of water, specific heat capacity of water, times 50, which is the initial temperature of water, minus temperature at equilibrium, or temperature of the mixture, must be equal to the heat gained by the body. But what is the heat gained by the body? We are told that the water at 50 releases 30.5 kilojoules of heat energy. So 30.5 kilojoules of energy is what will be gained by the other body. So we equate this to 30 0.5 times 10 to the power 3 joules of heat energy. That will be gained by the environment or other body. Is that okay? Now, having the mass of water, which is 250, 0.25 times 4,200 times 50 minus T must be equal to 30,500. Okay, 1, 2, 1, 2. So we have 0.25 by 42 by 50 minus T being equal to 30,305. Please help me determine T. Epia Boatma and could help me calculate for the value of T from the equation written on the board.
Um, 0.25 times 42 will give you 10.5, and 10.5 times 50 will give you 525.
So just solve it and then give me the final answer, T.
Okay.
20.9.
Pardon?
20.9.
I'm coming in. Therefore, T will be equal to 50 minus 29.05.
No, see.
20.9. So roughly 20.95. Hey, every about my
You said 20.95.
yes. Every about my who also called 20.95. Every you also had that. Oh, okay. So that's it. Hey, Charlotte.
Yeah.
Charlotte.
No, I have a question.
Okay, ask your question. Charlotte.
Mistaken.
Mhm.
Please, why did we subtract the final from the 50 and not the other way around?
You see, the water is at a higher temperature. Okay. So the water is losing to the environment, meaning the temperature of the environment is less than the temperature of the water. So if I am transferring to you, when we attain thermal equilibrium, where our body temperatures is the same, that's the temperature of the mixture. Okay. The temperature of the mixture will be less than the initial temperature of the hot body. So if I'm looking for the change in temperature for the hot body, it is its initial temperature, which is higher, minus temperature at thermal equilibrium. Charlotte, are you okay?
Yes, please. So it means in cooling, that's what we have to do all the time. You have to subtract the final from the initial.
It depends. Don't forget that over here we're not giving the initial, we're not giving the initial temperature of the body that is gaining. Okay. If we had been given, let's assume the initial temperature of the body gaining is T1, then it would have been M mass of the body, specific heat capacity of the body times. Now, because this body, cooler body is gaining, the final temperature equilibrium will be greater than its initial temperature. So it would have been T final temperature at equilibrium minus the initial temperature of the body that is gaining. Okay, but we were just told that water releases this amount of heat in cooling. That is why we equated this to that. Charlotte, please, are you fine?
Yes, please.
Equia, but Equia Adma.
Sylvia, please, the specific heat capacity given was joule per kilogram per Kelvin. And the question, the mass of the water was 250 grams. So in this case, are you supposed to just leave it in 250 grams or change it to kilograms?
So I can do it once the specific heat capacity of this was joule per kilogram per Kelvin. Okay. The reason for which I quickly change this to kilogram. If I want to use 250 gram, then this will change to joule per gram per Kelvin. It would have been 4.2. Are you okay?
Yes, please.
Using this would have been 4.2 joule per gram per Kelvin. Then I will use 250. But if I'm using joule per kilogram per Kelvin, then I must change this to kilogram. All right. Is there any other question? All right. Then there's a second question. The same NOVDEC 20. There's a second question. That is D. D. We'll solve the definition, but DII, an immersion heater of resistance R, draws a current I from the mains to vaporize 25 grams of water in time t. If the specific latent heat of vaporization of water is capital L, show that T is equal to L over 40 I squared times R. Start work. 5 minutes. In 5 minutes. The same question, the D part. We are using the concept length to solve Wassce problems. Please, those of you who just joined, I've highlighted on the question, so take notes. It's 10:37.
Mr. Dia, please, which one are we solving? The DII?
DII, yes.
Okay.
Problem of the day. Okay, let's see. An immersion heater of resistance R. So the resistance of the heater is given as big R. Draws current. So current I from the mains to vaporize 25 grams. To vaporize 25 grams of water in time t. If the specific latent heat of vaporization of water is L equals heat of vaporization. Show that T is equal to L on 40 I squared R. That's the problem. Now, so heat energy, but this heat energy is provided by electrical energy. And so electrical energy is what provides the latent heat of vaporization, QV. Electrical energy equals latent heat of vaporization, QV. Electrical energy is given by power times time. Power is also equal to current times voltage times time. So it means that IVT must be equal to latent heat of vaporization is given by M mass times specific latent heat of vaporization of the substance. Okay, that is all. Now the mass we are told is 25 kilograms. 25 kilograms. So you see, because V is not given, from Ohm's law, V is also equal to IR. So we'll substitute IR in place of V. So we have I squared RT is equal to MLV. Please, this V is a subscript to denote vaporization. Therefore, the mass is 25. Let's change 25 grams to kilograms. So 25 divided by 1,000 L. Latent heat of vaporization was given as L. If this is the case, then 25 goes into itself 1, 4. So 1 over 4 L. Then let's make T the subject. If you make T the subject, you have T is equal to L over 4I squared R. Hold on. Is that 40? Oh, okay, okay. Sorry. Yes, it's 40. 25 goes into 104. 25 will go into 104. So we'll have 40I squared R. Please, is that okay?
Yes, please.
That's the solution. If you want any explanation, let me know.
Mr. Yeah.
Hello.
You represented the QV by P.
You see,
What does P stand for?
P is this is using not the method of Mr. but using electrical energy. So the heat energy which vaporized the water was provided by electrical means. Okay, and can you hear me?
Yes, please, I can hear you.
And electrical energy which supply the heat energy is given by power times time. Power can also be broken down to IVT. It can further be I squared RT. Okay, so this electrical energy is what provided the heat energy which it did the melting. So the reason for which we are equating this electrical energy to the latent heat of vaporization ML. You let me indicate it with ML, but the V just to indicate vaporization. Charlotte, are you okay?
Yes, please.
All right. Then let me look for one of the troublesome questions. Wassce, I saw one interesting question. So Wassce 2021. I'm coming. Okay. This is not so troublesome, but I want to see how you can attempt it. Wassce 2021. Let me forward it to the group. This one. Wassce 2022, and we are answering the B question. The B question. Heat supplied steadily at the rate of 120 watts to 60 grams of ice raises its temperature from negative 20 degrees Celsius to 0 degrees Celsius in 200 seconds. Heat supplied steadily at the rate of 120 watts to 60 grams of ice raises its temperature from negative 20 degrees Celsius to 0 degrees Celsius in 200 seconds. Calculate the heat capacity of the ice. Specific heat capacity of the ice. Time it will take to melt all the ice at 0 degrees Celsius at the same rate of heat supply. Take specific latent heat of fusion of ice to be 336 kilojoules per kilogram. So the B question starts with this. I'll give you 8 minutes.
Like we are doing I.
Yes.
Hey.
Charlotte, keep quiet and suffer.
Yes, please.
Let's discuss. So whilst we discuss, you will be doing the marking. Okay. So heat supplied steadily at the rate of 120 watts to 60 grams of ice raises its temperature from negative 20 to 0 degrees in 200 seconds. So the heat supplied raises its temperature. So this is about sensible heat. Any heat that results in changing the temperature of a body. And we are to calculate the specific heat capacity. Okay, this is heat capacity and then the specific heat capacity of ice. So since we were given the power and then the time, the energy, okay, the heat energy supplied to the ice will be, the heat energy will be equal to energy supplied. Heat energy supplied will be equal to the power times time. And so PT is equal to MC delta T. The power is 120 watts. The time is 200 seconds. Here we are asked to calculate the heat capacity first. So MC changes to big C. So big PT is equal to the heat capacity times the change in temperature. Therefore, the heat capacity is equal to 0. Change in temperature is 0 minus 20.
Minus 20.
Yes. So we have 20 C 120 by 200. Therefore, C will be equal to 120 by 200 divided by 20. This. So C will be equal to 1200, okay, Joule per Kelvin. How many of you got this? How many of you got this? That if you had this, start marking. Start marking. With the correct unit, please. Charlotte, is it a question or?
No, you asked who had it
Okay,
correct.
okay. Then we are to determine.
Sir, Anastasia,
Hello, Stephanie.
please I have a
Okay.
So why didn't you take into consideration the mass of the ice when we're calculating?
You see, the reason is that he said we have to determine the heat capacity. Okay, heat capacity. And heat capacity of a body is given by the heat capacity C, big C, is given by the quantity of heat energy to raise its temperature by the change in temperature. So for the heat capacity, we are not interested in a certain mass. We are interested in quantity of heat energy that will be absorbed by the change in temperature. Now, if we are looking for specific, then that is when we consider any given mass. Are you okay?
Yes, please, thank you.
So we are to calculate for the specific heat capacity. And heat capacity connects to specific heat capacity by MC. MC. Therefore, if you know 1 kilogram, the heat that must be absorbed by 1 kilogram, you can equally calculate for the heat capacity of the body. So the specific heat capacity of the body is therefore equal to the heat capacity divided by the given mass. So 1200 divided by, what is the given mass? The given mass here is 60. Okay, and 60, I must change it to kilograms since I've changed, all values are in SI unit. So divided by 1000, 0.06. Okay, so this will be in Joule per Kelvin. This is also in kilogram. Yes, calculate this for me.
20,000.
Joule per kilogram per Kelvin as a specific heat capacity. Please, is there any question? Is there any question? All right, then the last question. The last question demands that calculate the time it will take to melt all the ice at 0 degrees Celsius at the same rates of heat supply. This time, you see, this one's was about sensible heat, but the question now is about latent heat, change of states. Okay, because it talks about melting, and we are told that the energy supply is at the same rate. So Q therefore will be equal to MLF. Okay, so PT is equal to MLF, and we have to calculate for the time. The power is 120. Okay, 120. So 120 times the time will be equal to 0.06 kilogram times the latent heat of fusion times 336 times 10 to the power 3. Please calculate the time for me. Come again.
168 seconds.
158.
68.
168 seconds. That will be the time taken to melt the mass. Please, any question here? Any question? All right. The last question. The last question. As for this one, it's a bit, whoever gets it will be rewarded. I forwarded it, the last highlighted question. Charlotte, as for this one, when you get it, you are going to Dubai.
Hey.
Hmm.
Hey.
Yeah. The question D. The D question. Water of mass 0.4 kilogram loses 210 kilojoules of energy when taken from the Earth surface to mass of surface temperature negative 60 degrees Celsius. The water temperature decreases until the water freezes. The water temperature decreases until the water freezes. The temperature of the ice formed decreases until it becomes equal to that on the mass. Calculate the temperature of the water while on Earth. Calculate the temperature of the water while on Earth. You are given the specific latent heat of fusion of ice to be 3.3 times 10 to the power 5. Specific heat capacity of water 4200 joules per kilogram per. Then the specific heat capacity of ice. Okay, so this is the problem. You are calculating the temperature of the water whilst on Earth. Okay, think through it for me. 5 minutes. Charlotte, when you get it correct, you go to Mars. In fact, you go to Mars, where your temperature will drop to -60. So start work. I'm giving you 8 minutes. 8
Mistake.
minutes. Hello.
Because you know I'm not getting it right. You see the way I promise him.
Oh, it's about Mars. You go to Mars. So let's see what you can do within 8 minutes. Start work. Think through. It's fun solving such a question. Honestly, it's not so difficult, but you must, be able to think through it very well to get it. So I want to see how you can do that thinking before I come in. Enjoy yourselves. Do not sit on the fence, please. Get what must be done. So, water of mass, Watman got 16.4. Who else, if you manage to finish? Who else got something? Akuya got 16.4.
Miss Lydia, please. I had a figure.
You had what?
I had a figure.
What did you get?
I don't know if okay, me, I had 18.57. I don't think I finished solving, but that's what I got.
Okay. So let's go through. Water of mass 0.4 kilogram loses 210 kilojoules of energy when taken from Earth surface to Mars of surface temperature -60. The water temperature decreases until the water it decreases till it freezes. Okay. Then the temperature of the ice formed decreases until it becomes equal to that on Earth, on Mars. Calculate the temperature of the water while on Earth. Okay, so the question implies that water loses, meaning water is at a higher temperature, and so it will lose heat energy of that magnitude, okay, when taken to Mars. Okay, the initial temperature we don't know, but we were further told that the water temperature decreases, meaning that once we are told that first the water temperature decreases, then we have sensible heat happening until the water freezes. So first sensible heat is happening due to the fact that the temperature of the water is decreasing. Then it freezes, change of state. So latent heat is involved here. Okay. Then, and latent heat, this change of state to ice occurs at a constant temperature. So it means that change of state must start at 0, which is the freezing point of water. Then the temperature of the ice formed decreases until it becomes equal to that on Mars. So sensible heat is also happening after the ice is formed. So it means that water goes through 3 stages. Okay. Decreasing temperature, okay, to 0. Then plus formation of ice. Then plus decreasing temperature to -60. These are the 3 stages. Class, are you with me? Hello, are you with me? So let's go through each one of them. So it means heat energy lost by water must be equal to the heat energy gain. And the gain is what we are giving as 210 kilojoules of energy. So said water of mass this loses 210 kilojoules. So we equate all the processes water must go through to 210 kilojoules. So let's look at the heat energy lost by water. Decreasing temperature to 0. So mass of water, specific heat capacity of water, times the change in temperature. The change in temperature, initial temperature, we don't know. Minus the temperature of the mixture. What is the temperature of the mixture? Class, what do you think will be the temperature of the mixture here? Let me pick your views. Stephanie, Uncle, Equia, what do you think will be the temperature of the mixture?
0.
Equia, why 0? Because the question is saying that once the temperature of the water is decreasing, then ice is formed. The ice further dropped. After formation of ice, it further dropped till the temperature becomes equal to the temperature at mass. Okay. So the temperature of the mixture, where the temperature of the water is equal to the temperature of the environment, will be -60. It will be -60. Are you okay here?
Yes.
Then, so this is the drop in temperature from the unknown initial, okay, to that. Then from that, okay, from there, ice is formed. So mass of ice times latent heat of fusion. Then plus mass of ice times specific heat capacity of ice, then times the change in temperature. What is the change in temperature? The change in temperature is 0. The final temperature of the, okay, 0 minus -60 temperature of the mixture. Please, do we understand? Don't forget, change of states. Change of states occurs at a constant temperature. So we have mass of water, specific heat capacity of water, times T plus 60 plus MLF plus M of I, C of I times 60. So let's put in the values. 0.4 times specific heat capacity of water, 4,200 times T plus 60 plus this mass of ice, mass of water is what we change to ice. So 0.4 times specific latent heat of fusion of ice, 3.3 times 10 to the power 5 plus the same mass of ice is what will drop in temperature. So 0.4 again. Then specific heat capacity of ice was given to us as 2100 times a change of temperature of 60. This we equate to the heat energy loss, 210 times 10 to the power 3 joules. So this will be the equation. 0.4, 0.4, 0.4. Okay, it's not showing at the other end. Okay, I thought it is also showing at the other end. So let's multiply, find the unknown T. So please calculate and then tell me the value of T. I'm also calculating though. This is 1680. T plus 60 plus this is 132, 132, 123. Then plus 0.4 by 210,
50,400.
50,400. Then 210,000. So 16.8T plus 60. Let's sum this up and send it to the other side of the equation. So 13200 plus 5040, which is this. So we have, this is equal to 21000 minus 18,240.
Which is 2760.
27. Okay, so this is 2760. Then 168 T plus 60. Let me be sure if I'm recording. Then let's divide through by 168. When you divide through by 168,
It'll be 2 plus 60 is equal to 16.43.
16.43.
Yes, please.
Therefore, we have t plus 60 equal to 16.43. Where have we gone wrong? Because this is giving us negative, which should not be so. It must be positive.
Mr. Dia, please, it's not 106, 168, it's 1680.
Where? 16.
80.
Please cancel.
80.
Oh, hold on, let me check. I canceled zeros at both sides of all the sides of the equation. Here, from here. Do you get me?
Okay.
Let's check our calculations. Let's check our calculations. Let's check from here. Please check these multiplications for me. 3.3 5. This times 0.4. So 2,000. 2,000. Then 0.4 times 2100 times 60. 5,400. This is 4 zeros. Okay. So that
Mr. Dia,
come again.
I was thinking about the addition of the 13200 and then the 5040.
Let's add. Okay, let's maintain this and then add them. 132,000 plus 5,400. This is 182,400. So let me clear it from here.
Mr. Dia,
Hello.
why is it that we multiplied with 260?
Why is it that
We multiplied 260.
260?
No, at the beginning, before we started that additional multiplication, we have 60. The 60 there.
Oh, I don't get you. Okay, I don't get you. Can you come again? I don't get you. So 18,2400 divided by 1680. I think the problem is from here. When you divide through by
Mr. Dia, please.
I'm coming in. When we divide through by this 1680.
Wait a minute.
It's 108.57. Please check for me. When we divide through by this, our answer is 108.57. Please, are you with me? Hello, are you with me? So T plus 60 is equal to 108.57. Therefore, T will be equal to 108.57 minus 60. Which is 48.57. Lizzie?
Mr. Dear, but you didn't subtract the 1824 from the 21,000.
We haven't.
Yes, we haven't. We just added it. Yeah.
Oh, okay. So hold on. Oh, okay. So 18240 is just summation, right?
Yes.
Yes, it's supposed to be just 10. So from that place, then it will match.
I get you. You should have drawn my attention quickly. So what she's saying is that we did not subtract the sum. So it means that 210,123 minus that 18 what? When you sum this up, 18.
18240.
240.
Yes.
One,
Are you maintaining the zeros?
yes,
Oh, okay. Then another 0.
because I'm not canceling through by. And so give me that subtraction.
27,600.
So when we divide through by 180, 1680.
164.3.
164.3. Okay, therefore, T plus 60, which is equal to 164.3. T will therefore be for 164.3 minus 60, which is, I think, 74. Is that correct? Or 76?
No, it's 104.3.
Okay, 104.3 degrees Celsius, or when you change it to Kelvin. Amma,
Mr. Yeah, please. When I did the division, I got 16.43.
when
When I inputted it in the calculator, it gave me 16.43.
no, you see, when you use a calculator, you're inputting. Okay, sometimes your calculator will not understand what you have inputted. So to avoid that, it is always advisable to go through it step by step as we are doing. The problem usually comes up when it's about inputting these exponential figures. So please, I always advise you to go systematic. Else, if you want the short way out, your calculator may not understand what you have inputted. Is that okay? So that must be the initial temperature of the water on Earth. That must be the initial temperature on Earth. So what I want you to do is that please, there are lots of them. Spend time to go through it. When you have issues, let's send it, let's discuss. Okay, send them, let's discuss so you can. The next lesson or topic I want us to be looking at is on wave motion. Wave motion. So you must start reading something on waves. Please, can I clean the board? Yaba? Yaba, speak up.
Please.
Your voice is down.
The answer you got doesn't mean that the water was boiling when it was on the surface of the earth.
Yes, beyond the boiling point of water. Meaning this is The T is the temperature of the water on Earth before it was taken to Mars to drop in temperature. Is that okay?
Yes.
Can I clean the board? All right. So please, you see, what I've seen is that when you are handling these few exponential values and you are not careful, okay, you can easily get it wrong. And that's the reason why I think but I think we omitted something, because if we are canceling out zeros, it should still work. 0 is cancelled. This one will also reduce by 0, 0 throughout. Okay, so if we have 168 here, this is, so it's, I'm sure it's as a result of the addition. So when you are doing this, I beg you pay attention, else you may think you are doing the right thing, but only an overlook, a simple overlook can floor you.
And Mr. Dia,
Hello.
I think the cancellation, it should have been canceling 2 more of the heat heat capacity. That's the 21,000. So it becomes 210.
Yes. Oh, we didn't do that.
No,
No,
you just canceled 1.
no, hold on. Lizzie, multiply 0.4 by 2,100 by 60. Let's see if that will give you 5,400.
Yes, please.
And then it should still work.
Yes, I'm talking about the cancellation.
This is 4 zeros. But we
Yes.
canceled 1.
So, yeah, so 1, then you have to cancel 2 more of that one because you're canceling 3 from this side.
No, I canceled 1. Oh. 16,
1.
16, 180. Okay, so it should be 1 throughout.
Okay.
Yes. You can cross check after the class. Okay, maybe
All right.
in the course of addition we add somewhere.
Okay. Thank you.
All right. So wave motion. How many minutes do we have? How many minutes? Charlotte, how many minutes do we have?
Please, we have 14 minutes.
Okay, wave motion. Wave motion. Okay, so we associate wave to this. I'm waving at you. We also associate wave to wavy or curly hair. Why? Why do we associate wave to this repeated movement of the hand and then curly hair? You see, wave motion falls under simple harmonic motion or oscillatory motion. Oscillatory motion is about the repeated motion. It's about the repeated motion of a body. So whenever a body moves repeatedly, it is exhibiting a kind of oscillatory motion or wave motion. The reason for which when we do this is that the person is waving at me, because this is also a repeated something. The reason for which curly hair, you see a lot of this logolege macaroni-like thing on the hair, repeatedly. Okay, that is why we also associate wave to curly hair. Now, wave motion. What is a wave motion? Anything that is repeated, okay, and takes place at a fixed angular velocity is also described as oscillatory motion and a wave motion. Okay, so we define a wave motion as a traveling disturbance that carries energy from one point of a medium to another. Wave motion is defined as a traveling disturbance that carries energy repeatedly from one region of a medium to another. So a traveling disturbance that carry energy that carry energy repeatedly from one region of a medium to another. So in wave motion, energy is transmitted, not matter. I will explain. So in wave motion, energy is transmitted, not matter. You've all seen the ocean wave before. The wave which forms on the surface of the ocean. If I ask you what actually creates that ripples or that repeated thing, the wave which is formed on the ocean, how would you explain? What forms the ocean wave? Yes, anybody to help? What actually forms the ocean wave? The wave we see when we visit the seashore, what forms it? Lizzie, do you have any idea? Stephanie, do you have any idea?
Please don't use him.
The question is that I'm sure you've visited the seashore before.
Yes, please.
The wave you see on the surface of the ocean, what forms
Yes.
what forms it? Or how is it formed? Do you have any idea to share with us?
I think it's formed by tide.
Formed by
Tide.
what is tide?
Huh.
Herbert, Kelvin, can anybody try? Anybody else? Amma, okay, Amma, speak to us.
Please, I think the wind.
Is that what?
I said I think the wind.
The wind.
Mm.
Can you explain?
Hey, so please, as when the wind is blowing hard on top of the surface, and like the water reacts, like I don't know.
You don't know.
Yes.
Okay, it's actually, you're actually right. It's the wind. You see, the point is that when you go deeper into the ocean, the wind velocity is so high. It's windy at the inner part of the ocean. And this is the reason why when ships, okay, cargo ships offload goods. So when they are bringing goods to Ghana, whenever there is the need for them to go back and it is not going with load, it must be filled with sack of sand. The empty ship with no people on board, no items, must be filled with empty sand, sand, bag of sand. This is because that would ensure the stability of the ship whilst sailing. Okay. Okay, please let me call you later. If the ship is not loaded, there's the ocean, and it's just moving like this on the surface. A ship is such that a greater part of the ship must always be submerged. So if this is the ship, we must have a larger part of it within the water. If we happen to have all the volume or size of the ship just on the water surface, strong winds can just topple it over. Strong wind, meaning, Akuya, I'm coming. Let's manage. We'll close soon, okay? When you move hundreds and thousands of kilometers within the sea, the wind intensity is so high, okay? That is why the ship must be loaded if it is going empty, so that it will be stable, else strong winds can easily topple it over, okay? Now, all that I'm trying to say is that hundreds and thousands of kilometers, the wind speed or intensity is so much. Okay, Lloyd, just pay attention. In fact, we'll be closing soon. So listen to the explanation, then the problem will be fixed later. So it is this strong wind, okay, that blows at the inner part of the wind, which is transferred to the water. So the energy of the wind is given to the water body, and the water also transfers the energy repeatedly, so it dies out at the shore. So the wave we see on the surface of the ocean is as a result of the strong wind energy. Okay, this wind blows, transfers the energy of the wind to the water. The water subsequently transfers it on and on and on. So any wave transfers energy, but no matter. That is why there is formation of this wave, okay, at the seashore always, every day, but the sea never gets flooded, because it is not water that is pushed to the shore, but it is the energy of the wind. So a wave is a traveling disturbance that carries energy repeatedly from one region of a medium to another. In wave motion, energy is transmitted, but not matter. Okay, the tides are different. Okay, here we are talking about the wave you see on the surface of the ocean when you visit the shore. Please, is there any question? So, wave transfers energy, but not matter. Okay, it is not water that is pushed to the shore, but it is energy. But the thing is that, you see, whenever you visit the ocean or the shore, some waves may be such that it looks so monstrous. So you may think it is huge volume, but because the energy is traveling within water, okay, sometimes the energy the energy must dwell in matter. So the energy, due to its size, seems to be carrying huge volume of water. It isn't actually huge volume of water, but it is the magnitude of the energy that it carries. When you visit the shore, some waves are such that nobody would advise you to run away. Others are also such that you just stay. What you see, which informs your running away or your staying, simply is about the amount of energy it carries. All right. So types of waves. Let's look at the different types of wave or waves we have around. One, we have made mention of one of them, ocean wave. We can also talk about tidal wave. Then we can also talk about water wave or the ripples. I think one may be figuring out what is the difference between ocean wave and water wave. You see, an example of water wave is that when you drop small stone or pebble in water, that circular thing, okay, that ring concentric thing which is formed on the surface of the water is water wave. And clearly, I'm sure you agree with me that is different from the ocean and then the tidal waves. All right. Time is up. It's exactly 12 o'clock. So we'll end it here and continue on next week. Please, the assignment given earlier still holds. The deadline for submission, if you haven't submitted, is Thursday. May the good Lord be with you. Take care of yourself. Please, if you have questions, forward it to me via WhatsApp and I'll address it. Until we meet again next week. In fact, take care of yourself and bye-bye. I'll be waiting for assignments. And then please try your hands on the question. If you find difficulty, get back to me. Okay.
Okay, bye.
All right.